Hello and welcome to NASA's Kennedy Space Center on Florida's Space Coast. Thank you for joining us today. This is the Science News Conference for NASA's PACE mission, the most advanced ocean color and aerosol mission to date. I'm Catherine Roloff, NASA's press secretary for the Science Mission Directorate in the Office of Communications. We are less than 2 days away from a moment that will launch us into a new era of Earth science. NASA is sending PACE to low Earth orbit to examine Earth's atmosphere and living ocean through a rainbow-colored lens. Today, I'm joined by a panel of experts to give you a broad overview of PACE's science. Kate Calvin, Chief Scientist and Senior Climate Advisor, NASA Headquarters. Karen St. Germain, Earth Science Division Director, NASA Headquarters. Jeremy Werdell, PACE Project Scientist, NASA Goddard Space Flight Center. Andy Sayer, PACE Atmospheric Scientist at NASA Goddard Space Flight Center. And Natasha Sadoff, Satellite Needs Program Manager, NASA Headquarters. Thank you to the media for joining us today. We'll be taking your questions right after opening remarks from our mission experts. Those of you watching online can submit a question at any time using the hashtag AskNASA. Now, over to Kate Calvin to start our discussion.
Thank you, Catherine. I'm really excited to be here, and I'm really excited for PACE. PACE is our first Earth science launch of 2024. But before we talk about PACE, I want to talk about 2023. So a few weeks ago, NASA, along with several other science organizations around the world, announced that 2023 was the hottest year on record. Collectively, the last 10 years have been the hottest since modern record-keeping began. We're seeing more hot years and an overall trend in warming driven by greenhouse gases, including carbon dioxide. As carbon dioxide is released, some of it is absorbed by land, some of it is absorbed by the ocean, and some stays in the atmosphere, trapping heat. Greenhouse gases aren't the only factors affecting temperature. There's also these tiny particles called aerosols that reflect or absorb sunlight and also affect cloud formation. PACE is going to provide more information on oceans and atmosphere, including providing new ways to study how the ocean and atmosphere exchange carbon. It's also going to give us information on aerosols. In addition to the information PACE will provide that helps us understand long-term climate, PACE will also give us information about oceans and air quality that can help people today. And you're going to hear more about the PACE science from the experts that speak after me. So to start the video, PACE is going to join the more than 24 satellites and instruments in orbit that are monitoring our planet. We can see things like vegetation, carbon dioxide, clouds and precipitation, and much more. And PACE is going to provide a complement to the existing observations that NASA has today. So just as one example, we launched a satellite called SWOT a little over a year ago. SWOT, or the Surface Water and Ocean Topography Mission, tells us more about how the ocean moves, including the height of the seas. PACE is going to give us information about what's living in those surface oceans, and much more. NASA's vast, decades-long array of data about the Earth is freely available today and provides a real-time living history of our planet. And PACE is going to continue that trend. So PACE's data will be open source and available no later than 60 days after launch. All of NASA's Earth science data is publicly available today, and we're taking steps to make that easier to use, including developing tools and resources that can help people understand what's happening in their communities today, what might happen in the future, and help them take steps to respond to those changes. As part of that effort, we launched the Earth Information Center last summer. The Earth Information Center includes a physical space in Washington, D.C., where you can come inside and see what's happening on our planet and how it's changing. It also has online resources for those of you that can't make it to D.C. So if you go to earth.gov, you can see more about the Earth Information Center. So I want to close by thanking the PACE team for getting us here today. I'm really excited for the next 48 hours and all the science that's to come in the next coming years. And so now I'll turn to Karen St. Germain.
Thank you, Kate. It is such a thrill to be in the run-up to launch, but as exciting as that is, what I'm most excited about is that PACE is going to so profoundly advance our understanding about how our oceans work and how they are related to the broader Earth system and the changing climate, as Kate mentioned. When PACE joins SWOT on orbit, this is going to usher in really a golden era in ocean science, because as as SWOT teaches us how the oceans work physically, PACE is going to show us the biology of the oceans at a scale that we've never been able to see before. It's going to teach us about the oceans in the same way that Webb is teaching us about the cosmos. If we, in the graphic that will pop up here, PACE will join SWOT and our whole fleet of Earth science missions. There's over 24 of them, observing oceans, land, ice, and the atmosphere to really show us how the Earth works as a system. Many of these missions, however, are nearing end of life, and this is part of what we do at NASA, is we innovate to bring new missions that will both carry on the work of those that are approaching the end of their life and also advance the science. PACE will also pave the way for future missions, such as the Glimmer mission, the Earth System Observatory Surface Biology and Geology mission, the Atmosphere Observing System, and future partner missions that will further advance our understanding. The science from PACE, really, I'm most excited about two things. One, PACE will dramatically advance our understanding of the the relationship between aerosols and clouds and the global energy balance. This is one of the biggest sources of uncertainty in our ability to model the climate. Andy's going to talk to you more about that and more about aerosols. We're also going to learn a tremendous amount about ocean biology. This is going to really center around understanding phytoplankton, these very small little beasts that live in little plants that live in the ocean that are at the foundation of life in our oceans in general. And Jeremy's going to talk to you more about that. But these advances in science also lead to advances in operational services. Often these services get delivered through partnerships with our sister agencies. These are advances in our ability to predict weather, visibility, and air quality. And that's why PACE is really a great example. It embodies our Earth Science to Action strategy at NASA, which is developing technologies and innovation that allow us to see things we've never been able to see before. Those observations lead to understanding, which gets captured in models, which gives us the ability to project into the future. And that really is foundational to the services that many Americans and people around the world rely on. These practical applications of PACE will most dramatically affect our coastal communities and industries. The ocean economy accounts for about $350 billion of the U.S. gross domestic product and for about 3.1 million jobs in the country. It's one of the fastest growing sectors in our economy, actually. And PACE will allow that sector to be informed by the best science we have, mitigating also adverse impacts on that economic sector, such as those that come from harmful algal blooms at about a cost of $50 million a year. So I'll close with one more thing that I'm most excited about with PACE, and that is that missions like this that you can only do from space show us our planet in a way that we can't see it any other way. Our home planet is a gem. And the image behind me gives you a hint at what we're going to see from PACE. This is off the coast of Brisbane. You can see eddies and coral reefs and aerosols. PACE is going to add another dimension to this beauty and show us a way, our home planet like we've never seen it before. So let's see. I think I'll hand off to Jeremy here. He'll talk to us more about the biology and the ocean science.
Thank you, Karen. If I may, I just want to take a deep breath and say, wow. Our community The shoulders we're all standing on in ocean color and atmospheric science started thinking about a mission like PACE 20 years ago. That's a long time given we're 2 days from launch, and spent 9 years building this mission with a project for which I'm incredibly grateful. So there is greater than a 50% chance I will burst into tears at some point during my 5 minutes here. So just bear with me on that. I think it makes for good film. So, all right. So getting back to the science part one, I mean, what we're doing here with PACE is really the search for the microscopic, mostly invisible universe in the sea and the sky, and to some degrees on land too. So you've had a really nice introduction on how this all fits in, but if we sequence to the next visualization, you'll get a peek at this beautiful, beautiful observatory we're going to launch in a couple of days. She might not look like much to you, but oh man. So it's a 3-instrument payload, and frankly, the technology really just operates like your eyes do. We are looking for interactions of sunlight, photons, quanta, with the atmosphere, ocean, and land. And whatever those photons touch, they get absorbed or they get scattered, and then you see, or the instrument sees what they are. And that is information that can tell you what's actually there. So it's as simple as that. We collect photons from the sun. Just collect them, collect them, collect them. 3 instruments, like I said. The primary instrument is the largest one on the back. It's the Ocean Color instrument, and it was built at NASA Goddard Space Flight Center. And then there are 2 small multi-angle polarimeters that you can see on this, or you could have seen on the side. The first, HARP-2, is a contribution from the University of Maryland, Baltimore County, not too far from Goddard, so fabulous partners and nearby. And the other is SPEX-1, a contribution from a consortium of organizations in the Netherlands. And while they're a little bit further away, they have been unbelievably wonderful partners for our mission. So we're very grateful for all of them. All right, back to science part 2. When I think about what PACE offers to the world, it comes in 2 words: connectedness and discovery. Connectedness because we are studying the combined Earth system. It is not an ocean mission. It's not an atmosphere mission. It's not a land mission. It's an all of those things mission. And that is so incredibly important because you can't understand one without understanding the other. And discovery, frankly, the scientific community with PACE has something they can grow into. And that hasn't happened in a really long time. There are amazing fleets of satellites out there, and I am unequivocally biased, but this is a mission that we don't know what we're going to learn about. And that is so deeply exciting. In fact, I wish I were a student again where I could be part of that. I'm too old, but what we're offering is just going to be remarkable here too. All right, so I mentioned the microscopic universe. In the atmosphere, those are atmospheric aerosols. They're basically particles like sea spray, sand, urban soot. Andy will talk to you all about them. I'm going to talk to you a little bit about the ocean. Why do we study the ocean? Well, it not only provides food that we eat and air that we breathe, but it helps regulate climate and weather. The ocean provides compounds that are used in medicines. And then, of course, the economy, jobs, fisheries, beaches, all of that, we rely on the ocean. So on these massive scales, short term, things that affect our everyday life, all the way to long term, those things that on a decade scale influence our quality of life, the ocean is incredibly important. So the microscopic upper ocean universe we search for are phytoplankton, as Karen mentioned. What are phytoplankton and why do you care? Well, they operate just like land plants. Through photosynthesis, they convert carbon dioxide into cellular material, so they form the base of the food chain while producing oxygen. They come in all different shapes and sizes. They taste different, so the fish tell me. They sink at different rates. Some get recycled in the upper ocean. Some can get to higher trophic levels or get eaten. Fecal pellets, poop, sinks to the deep ocean, and then carbon dioxide is removed from the system. So the community is really, really important because they all play different roles in the ecosystem. You have those that are beneficial, and as Karen alluded to, you have those that are harmful. And this gets back to the scales that we care about. Climate. As carbon moves through the system through phytoplankton. That's incredibly important. Shorter term, fisheries. Fisheries rely on the base of the food chain, thus phytoplankton. Switching over to economy, fisheries obviously, but also these harmful ones that contaminate drinking water, closed beaches, closed shell fisheries. You know, I think some order of 60% of the world or 50% of the world lives within 60 miles of the ocean. So you don't see it every day, but it does touch your life. So if you're a citizen of the world who likes breathing and you like eating and you like going to the beach, say thank you to a phytoplankton next time you see one of them. All right. Where does PACE fit into all of this? If we go to the next visualization, you will see what I could sit and watch for hours and hours on end. It is 25 years of watching the Earth breathe, collected by 3 different satellites that operate very similarly to how those on PACE will. And 2.5 minutes of your senses compressed into space watching the pulse of this planet. So the color bars, let me describe them. On land, fairly intuitive in the sense that white is ice, desert is brown, and greens are forests. If you move to the ocean, the purples, way, way offshore, those are the deserts. Why are the deserts important? Well, if you were to accumulate every phytoplankton and pile it up and then compare it to all the biomass on land plants, it comprised less than 1% of all of that, and yet it is still a community of algae, bacteria, and plants in the ocean that are responsible for 50% of all the production on Earth. That is a massive contribution by these small and mighty, beautiful, beautiful organisms. Back to the color bar. The reds, the greens, the yellows are all the forests. And if you know what you're looking at, you can see them expanding and contracting, getting richer or more intense. And so this is just change. It's change that's happening that we can only see from the vantage point of space. I can tell you, having been on boats, you cannot be everywhere all at once in the ocean. It's three-dimensional fluid, and phytoplankton turn over and change and grow very, very quickly. Now, what you're looking at is a presence-absence kind of scale here. If you see those colors, I'm telling you there are a lot of phytoplankton, or there are few phytoplankton. The purples are few, the reds and greens are a lot. I haven't mentioned to you what's there, and that's where PACE comes in. For the first time on global scales, we will be able to transform what you're seeing in this visualization. I'm pointing around because I don't know where you're seeing it, but you will now be able to say, I see the abundance and the presence of absence of particular communities. And tying that all the way back, now we'll know where the harmful ones are, where the beneficial ones are. Where the beneficial ones are moving to is the oceans are starting to change. Okay, so that's me. I love this stuff, and I'm going to turn it over to Andy now to get to the microscopic universe of the atmosphere.
All right, thanks very much, Jeremy. So my job is the A and C in PACE's name. That's aerosols and clouds. So I'll start with clouds because they're easier. Everybody in here, hopefully everybody knows what a cloud is. If we go out this door and we look up, anywhere in the world, there's about a 2/3 of a chance you're going to see one at any given time. Sometimes they're made of liquid water droplets. Sometimes they're made of ice crystals of various different shapes. Sometimes it's a bit of both. We care about clouds because we experience them in our daily lives as weather. Also, they can unfortunately bring disaster in some forms, thinking about hurricanes. So obvious, that's why we want to monitor them from space. But what are aerosols? And why are we bringing these 3 communities of aerosols, clouds, and ocean color together into one mission? Well, if I say the word aerosol to you, you're probably going to think of a deodorant spray can, maybe some hairspray, or like a rattle can with some paint in it. And those are all aerosols. But what we're interested in is kind of a whole different scale of them. And in this visualization that's going to come up right now, I'm going to show you a whole bunch of different types. Okay, so this is a model simulation showing different types of aerosols. We call them species all across the globe. So we don't have something like this from space yet. The different colors are the different types of aerosol, and the intensity of the colors tell us how much is there, right? So right now we have a pretty good handle from satellites on what is the total amount of aerosol, but we don't have such a good handle on how it splits down into all these different species. And there's lots of reasons that we want to know that. So what are we looking at here? Well, over the open ocean, you see all these kind of the swirls in blue. They're sea spray aerosols. So if you ever take like a long walk on the beach with your loved one, you take in a deep breath and you get that tang in your nose, that's an aerosol. Maybe in the winter you go to your backyard, you have a little bonfire. Maybe in the summer you pull out the grill. The next day your clothes are all stinky. That's smoke. That's yet another type of aerosol. And there's many more than that as well. In this visualization, you'll see things like desert dust. You'll see carbon from other sources like industry as well. You'll see sulfates, and there's other things too that aren't included in this model. There are things like volcanic ash, pollen is an aerosol too. It's a whole spectrum of different things. So why do we care? Why do we need to know these different species of aerosol, how they're distributed? Well, it's so dynamic. Space is the only way you can possibly do this. It's easy to, lose yourself just in the worlds where they're coming to, where they're going, and how they're changing in time. But I'm going to give you 3 specific reasons why I care about aerosols and why you should too. The first one is air quality and human health. When a lot of aerosols are at ground level, or nose level rather, they can harm people in specific ways. They can contribute to chronic conditions like asthma. And what really is a big determinant of how harmful different aerosols are you is what they're made of. So again, going from knowing just the total amount to its composition and how high it is in the atmosphere, that's really going to tell us where are the hot spots for bad air quality. We can see some of them now with ground monitoring sites, but just like Jeremy said, for oceans, you can't be in a boat everywhere all the time. You can't have a ground monitor everywhere all the time, so space is the only way we can do this. And we can't fix the air quality problems unless we know, where they are. The second reason that we really care about aerosols, and particularly why it's important for PACE, is atmosphere-ecosystem interactions. Aerosols in a lot of parts of the world, they can travel thousands of kilometers, and when they fall out of the sky, either under their own weight or being rained out, wherever they land, they can influence that. So dust aerosols in particular, they're often from iron-rich soils. They often contain a lot of phosphorus as well. And if those fall into a region of the ocean where there's not much of those nutrients, or if they fall to an area of the land where it's also kind of nutrient poor, they can fertilize plankton blooms. They can contribute to the growth of new plants. And again, we can't understand what our ecosystem is doing, where it's getting these nutrients from, unless we're able to monitor them from these sources to these sinks. And the third reason I want to talk to you about aerosols is tying right back into the 3 aspects of this mission, clouds. Although it might not seem like it, clouds don't form out of a vacuum. Cloud droplets tend to condense around aerosols. We call them cloud condensation nuclei for that reason. And how efficient an aerosol is at doing this, again, depends on what it's made of. So again, knowing exactly what types of aerosols we've got, where they are, where they're coming from, that's going to help us better understand where clouds are forming. How long is it going to be before they rain? How high are they going to get? There's lots of kind of like, big picture areas where this is true, but there's a few kind of very specific areas as well where we really care about stuff like this. For example, a lot of hurricanes hit the U.S. from the Atlantic, right? What's at the other end of the Atlantic? The Sahara Desert. A lot of dust is coming off, and the interactions between the kind of the dust heating in the atmosphere can really are thought to be able to help control cloud formation and how these storms move and how they grow. So the better we can get a handle on that, maybe the better we can predict these kind of severe events happening further out and get better forecasts. So that's why I care about PACE. That's why I was super excited to join this mission all these years ago. I want to pass you on to Natasha, who's going to tell you more about the application side of things.
Thanks, Andy. I'm also just so excited and so honored, and I hope I also don't get emotional, even though I've only been, it's been a couple of years, so I can't imagine those of you who have been the 20-year run. So we've heard a lot about applications already, which makes me so excited. There's so much innovative science and so much that we know and so much that we don't know that's going to come out of this mission. So the community is also really, really excited. And with that uncertainty just comes the opportunity for learning so much. So there's a visualization that will pop up in a second. You've heard about really a lot of these things, but just to revisit, PACE is covering the entire globe, land, water, the entire globe. And that's very unique because there's so many applications that are related. There's so many applications that PACE can speak to that we'll see in a holistic way. So you've heard about harmful algal blooms. You've heard about phytoplankton as the base of the food chain. So understanding, what's in the water, who's in the water, how is that impacting our health, our ability to go to the beach, the health of our dogs that like to swim in the water. So understanding what's in the water can impact so much. Even looking at fisheries, looking at aquaculture, if we can understand the phytoplankton and what kind of communities are in the water, we can better understand where we should site some of those aquaculture sites. Where are the best places to put our fisheries? Moving back a little bit onto land, we can also, as you heard, understand more about air quality. So there's a lot of communities that are interested in PACE data to better understand how air quality will impact our health. So air quality alerts, we can make them better. We can forecast more effectively and more accurately how aerosols will impact us. Also on land, there's a lot that we'll understand about forestry and agriculture. So again, what we can't see with our eyes are a lot of pigments that can alert us to stress in vegetation. So a lot of people are interested from the Forest Service, from other parts of the government, from other parts of the world, how can we use PACE data to understand, where is there some sort of sickness in vegetation or in an agricultural field. And then finally, also disasters, thinking about volcanic eruptions, thinking about forestry, wildfires, and again, how that air pollution will ultimately affect us and affect other processes and climate impacts. So who's in this community? We've done so much work to understand who is also excited about PACE, who could be excited about PACE but doesn't know about it yet. So we've done a lot of, I guess, metaphorical knocking on doors, a lot of phone calls, and getting the community together. So it's just as diverse as PACE is. The community is that diverse. So we have everybody from researchers who want to bring PACE data into their models, all the way to the private sector, to members of the public who just want to ingest the best air quality alert they can, and everything in between, decision makers, policymakers, communicators, and each of those users have different needs. So we've done a lot of work to meet with those users separately and to understand how we can make PACE data actionable, useful, and accessible for them, because the answer is different for each of them. So we've given a lot of attention to how we can democratize PACE data and Earth observation data so that it meets all of their individual needs. So sometimes that could mean they're accessing it through a certain type of portal in a certain type of data format. So we give attention to all of those things to make sure that the innovative science that we've talked about gets into the right hands. We have an early adopters program where we have applied researchers that are already playing with simulated PACE data sets. I'm so excited that some of them are here at launch, which is awesome. So shout out to those that could join us. We also have a community of practice. So we have hundreds of people that are just waiting for updates, learning about PACE, calling into webinars, getting newsletters, and just also super excited to share with us how they want to use the data. So there's so much that we already know, but again, so much that we're learning, and we're going to continue to work with the community once we actually get the data a couple months from now to see, what don't we know? What can we do with PACE data that we didn't even think about? Because I think it's going to be a lot of exciting stuff to come. So thank you, and I'll pass back to Catherine.
Thank you to our experts. The phone line is now open. Please identify yourself, your outlet, and the expert you would like to answer your question. To maximize today's time, please narrow the questions to the PACE science mission only. Our first question comes from in the room. Are there any questions?
Ken Kramer, Space Up Close. Thanks for doing this. Very exciting mission. It's a lot to absorb. So one thing I'm wondering about is with these aerosols, will you maybe eventually be able to create clouds, rain clouds in drought areas? Is that kind of like a long-term goal, or is that just crazy?
I would say that's not within the scope of PACE. We're kind of purely observing the state of the Earth system as it is, with the idea then that can be used to improve our understanding of how aerosols and clouds work, how they interact. And I would say it's better understanding the processes themselves that is our main goal. weather modification is not my personal expertise. I know that's something that various institutions have tried in the past. But again, I wouldn't say it's something that we're specifically involved in.
Great.
Have you had any useful discussions with any of those weather modification people?
I have personally not, no.
Or anybody on the panel?
Well, I'll just say that that of course, as you know, this is an area of interest and conversation. Again, NASA's role is really trying to contribute to the foundational science, so that the institutions, the policymakers that are doing that thinking and that work have the best science and the best ability to understand how these systems work to inform those things, those conversations.
Part of your focus here is applications, so that's why I'm asking the question.
Yeah, no, and that's just not an application we've looked at yet, but it is a conversation that comes up, and it is something, if we see that PACE is relevant and a user came to us and wanted to discuss, we'd have the conversation, but we haven't targeted those sorts of users yet.
And we will be going to the phone next. Jonathan from Fox News.
Good morning, Jonathan Seri with Fox News. Thanks so much for doing this briefing. I have a question about logistics. How long is the PACE mission expected to last, and what type of orbit will PACE be in, and how does that orbit factor into how PACE will be gathering data from the Earth?
I can go ahead and hop in on that one. So the design life for the PACE mission was 3 years. One can think of that as the minimum, but very, very often our missions last much, much longer than that. We're carrying at least 10 years of consumables on PACE. That is the fuel we need to carry on the satellite itself to maintain the station keeping, and ultimately at end of life help make sure that that is safe. So we're hoping for a nice long life for PACE. Oh, and the orbit, do you want to? Yeah, go ahead and talk about the orbit.
Sure. So for the second part of your question, we are a polar ascending orbit, which means we start collecting data on the sunlit side of the Earth at the South Pole and then travel north to the North Pole. And then we will collect data over land, ocean, everywhere, as long as there is sunlight. Some interesting tests early on to see what is possible on the dark side of the Earth, but that's not our prime mission goal. Altitude is just shy of 700 kilometers. It's 676.5 kilometers. The coverage actually varies by instrument. So the primary instrument, the Ocean Color instrument, and HARP-2, one of the two polarimeters, are a very, very wide swath, and they will see all the real estate on Earth every day. The third instrument, SPEX-1, is narrow swath, and so it will take closer to 30 days to basically revisit the same piece of real estate. And where PACE fits in particular for oceanography, is that given the target are these transient creatures or plants, algae, they don't persist on the scales land plants do. It is incredibly important to get a view every single day, because what your target on land might be will probably be there tomorrow, but there's a really good chance the phytoplankton you're trying to investigate will not be. And if I could have the floor for 2 more seconds, just to share and go back to, this is why NASA does Earth science. You've heard the context and the texture of all of this, but this mission epitomizes it. The diversity up here alone in the science that's being accomplished is really remarkable. So I'm fanboying a little bit. I apologize.
Thank you. And now we'll go back to the room. Are there any questions? Yes, in the back.
Hi, yes, Will Robinson-Smith with Spaceflight Now. Thanks for taking our questions here. Going back to the application side of things, understanding there are early adopters and that you all have been reaching out to various organizations, government entities, and whatnot, if you start to see some troubling data forming just sort of within the team that is closely monitoring it, Are there mechanisms by which you can then sort of look at the relevant governmental bodies, whether they be state, local, federal, what have you, and then sort of create an action plan in conjunction with them, or raise their alert to say, hey, you've got something incoming, you need to start strategizing about it now? Thank you.
Maybe I'll answer your question in a couple of parts, hoping that it gets to what you mean. We're working a lot now on user readiness, on trainings, on materials, so that when the data are released, the community will understand what is in the data, what it means, how to use it. But we are hoping that the community will be able to do that on their own with our help if we can, and do with it what they seek to do. So we're not necessarily producing decision support tools or the types of tools that would give answers to certain questions that users are interested in. We're making the data available, and then there's various users are boundary organizations that have their own tools or models or portals that they'll bring PACE data in, and it'll be a data set that enhances what they already have. So I hope that gets to your question, but we're trying to offer everything we can so that users are ready and understand the data and its limitations, so that they can apply it for whatever purpose they want to.
Let me just augment that answer a little bit as well. Great, terrific answer. We talked about early adopters. One of those, for example, is NOAA, the National Oceanic and Atmospheric Administration. Agencies, so NOAA and agencies like that at the state level, they have that operational responsibility that you just mentioned. So this is a key contribution that NASA makes, often unseen. Behind the scenes, those forecast, watch, warning kinds of services that are often provided by other agencies are often fueled by NASA data, and we certainly expect that will be the case for PACE.
Thank you. And our next question comes from the phone lines. Jim from NASATech.net.
Oh, hi, everybody. It's Jim Siegel from NASATech.net. And many of my readers are in Florida or in other states that have a lot of lakes, and I assume that the PACE instruments are going to be looking at lakes as well as oceans. And particularly, I'd like to talk or explain to my readers a little bit about how this instrument is going to help from the fishing point of view. Is this going to help, for example, identify where fish beds ought to be established, or on the other hand, places where fishing is dangerous because of whatever plankton or chemicals or whatever? And I wondered if somebody could talk about that. Thank you.
Thanks. That's a really, really great question. Let me start with the lakes. So one thing we haven't discussed is the size of the footprint on Earth that we're going to see with any of the instruments. And so the ocean color instrument itself, the one that will be supersonic for the second part of your question, is roughly 1 square kilometer if it's looking straight down. So your lake or your target will have to be larger than that to get a meaningful retrieval from this particular observatory, that is PACE. But a study a colleague did some time ago indicated there would be order of 100 lakes in the contiguous United States, certainly Great Lakes, Lake Okeechobee. To your second half of the question, the answer is yes. So as I mentioned, one of the primary driving motivations for understanding how phytoplankton communities evolve at a temporal and spatial scale of meaning for day-to-day life is that fisheries do well with certain communities being present. That is, what eats the phytoplankton has a particular interest in certain kinds of phytoplankton, just like we all like to eat certain things and we seek that out. And then the fish that eat the zooplankton and on up the food chain, really get influenced by what's at the very, very bottom. And so when we're talking about retrievals that can show not just abundance of this food source, but also the community that is there, that information is incredibly relevant for somebody who might be making a decision about, do I need to move a fishery, establish a fishery? And then at another level, there are other data products in the aquatic universe that we can produce too that will basically refer back to how much suspended sediment might be coming in on a very wet year from a particular river or estuary or after a storm, the dissolved content of that too. So there are all these other matrices of information that would be useful for someone trying to make decisions. And I've actually had the opportunity to talk with shellfisher people that have started to use satellite data. So I think there is a ton of relevance. And getting back to a previous question, the data are freely available, as are the tools to use it, and in principal trainings as well too. So hopefully you can dive in and your readership will, discover the new tool in their toolbox.
And I can just add real quick just to that. Thanks, Jeremy. PACE data is meant to be one tool that users can add to their toolbox. So it's not going to give all the answers to all the questions. So we have early adopters who are using PACE data, really larger scale, like considering that 1 kilometer resolution, to look at fisheries and to look at where sport fishermen can go. But they'll use other data sets, ground-based data or even drone data to see, PACE maybe can identify a hot spot, good or bad, and other data can then point to maybe within that 1 kilometer where else they can go. So it's a data set that can provide some answers and not all, but it complements other available data sets.
Thank you. Now we will go over to NASA Social at #AskNASA on X for Kate Calvin. Question Quest asks, are we warming up as a planet? And perhaps you can also touch on how PACE helps us study climate change.
Yeah, thank you for the question. And yes, we are warming as a planet. So 2023 was the hottest year on record. The last 10 years have been the warmest since modern record keeping began. And if you look at a time series of warming over time, you will see a trend towards upward. There are still warmer years and cooler years that have to do with some of these natural cycles like El Nino, but we're overall seeing a trend. And that trend towards warming is driven by greenhouse gases, including carbon dioxide. And one of the great things about a mission like PACE is it's going to give us a better understanding of the exchange of carbon between the ocean and the atmosphere. So these phytoplankton that Jeremy talked about are really important in the carbon cycle. So they play an important role in understanding how much carbon remains in the atmosphere. And the more carbon in the atmosphere, the more heat we trap. PACE is also going to give us more information about aerosols, and that was mentioned earlier, and how they influence clouds. And so we'll have a better understanding of of climate over time, and that'll give us more information to better project that into the future.
Thank you, Kate. Now we will go back to the room. Are there any questions? Yes.
Yeah, hi, Bill Harwood for CBS News. And like Ken said, a lot of information to absorb. I was looking at the website, and it's gigantic. But in today's world, for some of us sitting out here in the audience, I can write a 600-word story, and then the editor is going to knock that down to 300 words, and then there's X or Twitter. So what I'm asking for Kate or Karen, how can you boil this mission down? This is impossible, but I'm asking anyway. Can you boil something this complicated down into a couple of very basic concepts so readers at least have a sense of what you guys are doing, if not the details?
Sure, I'll start and maybe Karen will add. I would think about it in a couple of different dimensions. One is what it will observe, so both ocean and atmosphere. And there, in both cases, we're looking at tiny things. So microscopic life in the oceans, tiny particles in the atmosphere. The second thing, and I think this came out a lot from the experts, is about time. So I talked about climate, but there's also near-term effects. So PACE is going to give us information that helps us plan today. It'll also give us information that helps us plan in the future.
Oh, yeah. So those are two really important dimensions to think about here. And I guess the other thing I would say is the oceans are 70% of our planet. The impact the oceans have on our lives is enormous. And yet the oceans are one of the least well understood parts of the Earth system. So the PACE as a mission is going to profoundly advance our understanding of how the oceans work and how life in the oceans is related to life on land.
Thank you. And now we will go to the phone lines. Emmanuel from Exploration Spatial.
Good morning. How are you? Thank you and congratulations on the mission. Looking forward to all the data. I think I will go along with Bill's question. There's a website, a NASA website. It's climate.nasa.gov, and there's an amazing dashboard there with the current status of the planet. So you can see key metrics like carbon dioxide, global temperature, methane. Is there any key metric or number that PACE can contribute or we can include in this dashboard? Or the data from PACE can allow us to fine-tune and improve these current numbers?
Dashboard. So let's see. So you mentioned our climate website. We're also, Kate, you mentioned the Earth Information Center, where we're trying to consolidate these dashboard metrics. I'll give one answer, and perhaps my colleagues here will augment. I think the state of biology on Earth is one key metric. The how much and how healthy kind of metric is one that PACE could certainly contribute to. You guys have more thoughts?
I can add one thing too. Just the dashboard you're mentioning is looking at, it's direct observations of particular things like temperature, carbon dioxide, sea level. What PACE is going to do is help us better understand how we got to those. So it'll help us better understand that carbon exchange between ocean and atmosphere that is behind the carbon dioxide number that we have there. So it'll give us the processes and a process understanding of what's included in that dashboard.
And then from that, you can effectively see how the living ocean is responding to all of these changes.
I fully agree with everything they've just said. The things we're looking at, they're so tiny, they change so quickly, but understanding them helps us understand how we get to the big numbers.
Thank you. Are there any more questions in the room? All righty, we'll go back to the phones. Jeff Faust from Space News.
Hey, good morning. Question probably for Jeremy or Andy. You've been working on this mission for a long time. You had some near-death experiences along the way with threats of cancellation. I'm curious, were there ever any doubts in your mind you'd be sitting here today on the verge of launching this mission? Thanks.
That's a Jeremy question. It has been a long, strange trip, as they say. Now, we were as confident as one can be that we would find ways to persevere. So the community wanted all of this. I'm not going to dive into policy or politics, but it's been a really remarkable journey, and the support from the community, the support from the agency, the support from people like yourselves asking questions and getting involved, we've kept our morale high.
Perhaps I'll just add to that one of the reasons that we do events like this, and we really appreciate the engagement, it is that to maintain support for missions like PACE, that really depends on us getting the story out there about the kind of science we do and why that's so important to communities at home and around the world, and it's important to our stakeholders, right? So I think one of the reasons we're sitting here today is because there were many in our stakeholders community who understood the potential impact of PACE and supported us moving forward.
And maybe I'll just add, that's why programs like the one that I work on, applications programs, exist, is to make sure that everybody, whether it's a family walking at the visitor center at Kennedy yesterday, or someone in the government, or someone in the research community, understands how PACE will affect them, and how we try to make sure to highlight those real world, those actual applications that impact all of us, whether it's wildfires or air quality or fish that you eat. I could go for a grouper sandwich after this. So there's very real applications that we all understand, and that my job is to communicate.
Are there any more questions from the room? All right. Well, thank you all. Thank you to the media for their questions and to our panel of PACE science experts. Please join us tomorrow at 9 a.m. Eastern Time for the PACE pre-launch news briefing. And keep the conversation going on social media using the hashtag #KeepingPace. Be sure to set your alarms early to watch our live launch coverage this Tuesday, February 6th, starting at 12:45 a.m. Eastern Time on nasa.gov/live. Thank you and goodbye from NASA's Kennedy Space Center. Go NASA, go Falcon 9, go Pace.
Go Pace.